Hello everyone. Today we are going to analyze this beam using flexibility matrix method. In this beam there are two spans, span AB and span BC. In the span AP there is a point load 80 kN in the center. In the span BC there is uniformly distributed load 60 kN per meter. It is acting for the whole span. Length of span AB is 6 meter and the moment of inertia is 1.5 I. Length of span BC is 4 meter and the moment of inertia is 2 I. In the point A, there is a fixed support. In the point B, there is a hinged support. And in the point C, there is a roller support. In this beam, the number of unknown reactions and moments are 4. In the point A, there is a moment MA and the vertical reaction RA. In the points B and C, there are vertical reactions RB and RC. The degree of static indeterminacy will be 4 minus 2. We will get 2. Let us release RB and RC. Here you can see that I have removed RB and RC. So the beam becomes a cantilever beam. This beam is called as released structure. Now let us draw the coordinates diagram. Let us keep RB as the first coordinate and let us keep RC as the second coordinate. We know the equation which is used in the flexibility matrix method. In this analysis, there are two coordinates. So inside the P matrix, delta matrix and delta L matrix, there will be two values. And the size of the flexibility matrix will be 2 cross 2. That means inside the matrix, there will be two rows and two columns. Our first coordinate is RB, so P1 will be RB, and our second coordinate is RC, so P2 will be RC. In the given beam, in the supports B and C, there is no settlement or sinking, so delta 1 and delta 2 will be 0. This is a zero matrix. We know that zero matrix is 0, so no need to consider that. In this case, we will have this equation. Now let us take the released structure. From the point B and C, we have released the vertical reactions RB and RC. In this case, these displacements will be the deflections in the points B and C. To find them, we are going to use the unit load method. In the unit load method, we have to make sections. In this beam, there are three different parts, AD, DB and BC. So we have to make three sections, one in AD, one in DB and one in BC. Here you can see that I have made three sections, one in BC, one in DB and one in AD. I have made all of the sections at a distance of x from C. Now let us make a table. First let us enter the members. There are three members, CB, BD and DA. For all of the sections, the origin is C. For CB, the limit is 0 to 4. For BD, it is 4 to 7. And for DA, it is 7 to 10. Now let us enter the flexural rigidity. In CB, the moment of inertia is 2I. So the flexural rigidity will be 2EI. For BD and DA, the moment of inertia is 1.5I. So the flexural rigidity will be 1.5EI. Now let us find the moment M. We are going to find all of the moments from the point C. In this case, we have to follow left-hand side rule. Clockwise will be negative and anti-clockwise will be positive. First, let us find the moment in CB. Up to the section, there is only uniformly distributed load 60 kN per meter. It is acting in the clockwise direction so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. So it will be minus 30 x square. Now let us find the moment in BD. Up to the section we have only uniformly distributed load. The UDL is acting in the clockwise direction so that it will be negative. It is acting for a distance of 4. So we have to multiply with the 4 and then we have to open a bracket. We have to divide the distance 4 by 2 and then we have to add the remaining distance. This distance is x minus 4. After simplifying, we will get this. Let us apply that. Now let us find the moment M in dA. Up to the section we have UDL and the point load. The UDL is acting in the clockwise direction so that it will be negative. The distance is 4. Then we have to open a bracket. We have to divide the distance by 2. Then we have to add the remaining distance. This distance is x minus 4. The point load is acting in the clockwise direction so that it is also negative. For this load, this is the distance. This distance is x minus 3 plus 4. So it will be x minus 7. After simplifying, we will get this. Let us apply that. Now we are going to find the moment M1. We need to remove all of the loads from the beam and we have to apply unit load at B in the direction of RB. First we are applying here because RB is our first coordinate. Let us find M1 at CB. Up to the section there is no load, so the moment will be 0. Let us find the moment at BD. Up to the section we have unit load. It is acting in the anti-clockwise direction so that it will be positive. For the distance we have to take this distance. This distance is x minus 4. 1 into x minus 4, it will be x minus 4. Now let us find M1 in dA. Up to the section we have only the unit load. The unit load is acting in the anti-clockwise direction so that it will be positive. We have to take this distance. This distance is x minus 4. 1 into x minus 4, it will be x minus 4. Now we are going to find the moment M2. Now we have to apply unit load in the point C. Let us find the M2. About all of the sections, the unit load is acting in the anti-clockwise direction, so it will be positive, and the distance is x. 1 into x, it will be x. Using this formula, we can find delta 1L. For CB, M1 is 0, so no need to do the integration. We can directly apply 0. For BD and DA, the flexural rigidity is 1.5 EI. So in the formula, instead of EI, we have to apply 1.5 EI. Using the calculator, we can do these integrations. For delta 1L, we will get this. Then using this formula, we can find delta 2L. For CB, the moment of inertia is 2EI. So instead of EI, we have to apply 2EI. For delta 2L, we will get this. Now let us find delta 11. Using this formula, we will find delta 11, which is 48 upon EI. Using this formula, we can find delta 12 and delta 21. For both of them, we will get 96 upon EI. Using this formula, we can find delta 22. For delta 22, we will get this. In these two matrices, we have found all of the displacements. We can apply them. No need to consider EI because it will be eliminated. Using a calculator, we can find the inverse of this matrix. For the inverse, we will get this. Both of these values are negative. So negative into negative, it will be positive. Then we can multiply these two matrices. After multiplying, we will get RB and RC. Now let us take the real beam. By applying this rule, we can find RA. Let us take a moment about C from A and find MA. Let us assume that MA is acting in the anticlockwise direction so that it will be negative. RA is acting in the clockwise direction so that it will be positive and the distance is 10. This point load is acting in the anticlockwise direction so that it will be negative and the distance is 7. RB is acting in the clockwise direction so that it will be positive and the distance is 4. The UDL is acting in the anticlockwise direction so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. For MA we will get a positive value. That means our assumption is correct. MA is acting in the anticlockwise direction and it is a hogging moment. Now let us take a moment about B from A and find the moment at B, MP. Let us assume that MP is a hogging moment. MA is acting in the anticlockwise direction so that it will be negative. RA is acting in the clockwise direction so that it will be positive and the distance is 6. This load is acting in the anticlockwise direction so that it will be negative and the distance is 3. About AB, MP is acting in the clockwise direction so that it will be positive. For MP, we will get a positive value. That means our assumption is correct. MP is a hogging moment. Now we are going to draw the bending moment diagram by superposition method. First, we have to assume every span as a separate simply supported beam. Then using these formulas, we can find the maximum bending moments and we can draw these two diagrams. Using the moments at A and at B, we can draw the end moment diagram. Since these two moments are hogging, the end moment diagram will be negative. Then by combining these two diagrams, we can draw the bending moment diagram by superposition method. Using the right hand side rule, we can find the shear force values. Here you can see the shear force diagram. In this point, the shear force becomes 0. For the span BC, in this point, there will be maximum positive bending moment. In this point, we can make a section and find the distance. You can see that in that point, I have made a section at a distance of x from C. We know that in this section, the shear force is 0. Using that concept, we can find x. For x, we will get 1.65 meter. Using the left-hand side rule, let us find the maximum positive bending moment. RC is acting in the anticlockwise direction so that it will be positive and the distance is 1.65. The UDL is acting in the clockwise direction so that it will be negative. We know that with the UDL we have to multiply the distance and then the distance by 2. This is the maximum positive bending moment at BC. The point C is a simply supported end, so the moment will be 0. Now let us find the moment at B. RC is acting in the anticlockwise direction so that it will be positive and the distance is 4. The UDL is acting in the clockwise direction so that it will be negative. With the UDL we have to multiply the distance and then the distance by 2. We will get minus 84. To find the moment at A, we can use right hand side rule. MA is acting in the anticlockwise direction so that it will be negative. Now let us find the moment at D. MA is acting in the anticlockwise direction, so that it will be negative. RA is acting in the clockwise direction, so that it will be positive, and the distance is 3. Finally, we will get 54. This is the proper bending moment diagram. If we make this diagram upside down, that is called bending moment diagram on the tension side. In these 3 points, the bending moment becomes 0. These are the points of contraflexure. We can make sections in these 3 points and to find the distances. You can see that in those points I have made sections. Using right hand side rule, we can find this distance. For that we will get 1.41. To find this distance x, again we can use right hand side rule. Using that we will get 4.17. Then to find this distance x, we can use left hand side rule. Using that rule we will get 3.3 meter.